Welcome to Section 4, where we'll discuss interoperability and working with third-party libraries. In the previous section, we saw how to improve the performance of our applications by understanding how memory is managed in iOS and by learning how to find and fix potential issues. In this section, we're going to learn how Swift implicitly bridges to Objective-C with the Cocoa framework. Then, we'll learn how we can utilize bridging headers to enable our Swift code to communicate with Objective-C, C, and even C++. We'll also see how we can utilize Cocoa pods to incorporate third-party libraries into our applications. Now we'll move on to the first video of this section, Implicit Bridging and Cocoa, which illustrates how Swift to Objective-C implicit bridging works. In this video, we're going to take a look at some similarities as well as some differences between Objective-C and Swift syntax. We'll see how each one utilizes the same Cocoa framework and how Swift types can implicitly bridge to Objective-C. Swift is a powerful, fast, and safe programming language that brings a lot of modern language features to the Cocoa framework. This, to many, has been a big sigh of relief for developing iOS and OS X applications. Unfortunately for Swift developers, the vast majority of OS X and iOS applications were written in Objective-C, and if you're planning on working as an Apple platform developer, you'll have to know how to interoperate with, at bare minimum, Objective-C. Swift provides seamless access to Objective-C's APIs, mapping all of your Objective-C code directly to Swift syntax. And since both Swift and Objective-C utilizes the same Cocoa framework, there's a lot of inherent similarities between the two. However, syntax is not one of them. Let's look at some examples of the implicit bridging that we get for free with Swift. Here we have Objective-C's UI document class, which we'll break down piece by piece. We'll start with the file modification date property, which is of type NSDate. In Swift, this declaration would look like this, which in Objective-C translates to this. We see our properties are defined with the @property keyword, followed by the type, and then the named pointer. We see here that Swift utilizes a forced unwrapped NSDate optional. This is because Objective-C doesn't contain the notion of an optional pointer. So, in order for Swift to use NSDate in the same manner as Objective-C, it needs to be explicitly unwrapped. Of course, there are mappings for all of Objective-C's other types as well, though unlike NSDate, most have slightly different syntax as shown here. Notice that ID gets mapped to an any object, and class gets mapped to any class. Methods are a little less straightforward. Here we have a Swift method, file name extension for type, and again the same method in Objective-C. Although the syntax is quite a bit different, we can see that these are clearly the same methods. Here, the name for our method is the same, along with the first and second labels and their types. And we have our return types. This is pretty straightforward. It does get a bit more complex, however, when we introduce blocks. Here we have a UI document save to URL method in Swift, and again in Objective-C. Swift's version is a bit cleaner. Here we have the external and internal labels, along with a less redundant completion handler argument. The big difference, however, is in the completion handler, which is called a block in Objective-C. Objective-C's blocks are bridged into Swift closures for us, which allow us to use Swift's modern trailing closure syntax. NS errors are an interesting case because Swift, in many cases, completely does away with the error argument and introduces a new feature to deal with errors. In Objective-C, returning a nil value represents a failure case. In that case, the outError parameter is populated. In other words, if our NS error parameter comes back non-nil, we know we have a problem. Swift removes the error parameter altogether and utilizes the new throws keyword, which tells us that the method has the ability to throw an error. Functions marked with throws should be called within a try-catch block to handle the error should one arise. We'll be looking closely at error handling in Section 6, Troubleshooting, Advanced Debugging, and Error Handling. By now, I'm sure you've noticed that Swift brings with it much cleaner and more succinct syntax than its Objective-C counterpart. We also see that the init methods are no exception. Notice that Swift removes the with file URL and instead sets file URL as its argument label. This is a consistent convention throughout Swift. If you ever need to convert an initializer from Objective-C, remember this pattern. Let's look at one last example before we move on to some demonstrations. Enums in Objective-C are declared as follows. Again, the same enum maps to Swift with a much cleaner syntax. Now that we've looked at how Swift's implicit bridging works, let's look at some examples of how we can expose Swift to Objective-C code and how we can use Objective-C in our Swift code. In this video, we looked at some of the similarities between Objective-C and Swift, and how they implicitly bridge to utilize the same Cocoa framework.